Alrighty, coming off the success of our previous change here that caused only the LED 1 and 3, so pin 3 and pin 6, to flash, and the pin 4 or LED 2 to remain constantly illuminated, let's go ahead and see if we can do something else here. Let's see what other changes we can make and see if maybe we can incorporate, say, one of the switches that's on there. See if that's an option. So how would we go about doing that? Since we have figured out previously that these are the pins that we need and that we can use the latch block E to set. But how do we figure out where the switch is associated with? And that is really from this document right here. So this is the development board user's guide. So it's going to basically have everything, a lot of stuff at the beginning here, just generic stuff that's in most of the microchip documents. So if we go down here to the bottom, or close to the bottom, okay, now I can see a picture of the board. I also want to mention, it is sort of interesting that this board doesn't look exactly like my board. So I'm not sure if maybe they superimposed this image on here, right here, or if maybe there was a slight version difference, or I really wouldn't think it would be a version difference. And the reason is because this chip really needs to be set up in a certain orientation, and that's an orientation that really can't easily be changed. So when I went through a video before, I said that this was pin 100 right here, and that pin 1 was right here, which means that the LED pins are right here and right here. I find that that is actually not correct. That when I look at my board, the dot that indicates where the starting and ending pins are is actually on the top left corner, right there, almost near that little dot symbol right there, that you would think actually is denoting, well, maybe that's denoting U9, I'm not really sure. But essentially you can kind of, if you zoom in here, it makes more sense actually based on the schematic here, that these two pins are associated with the LEDs, because basically it's this one right here, so these two leads. So you can see that they come over to right here, and most likely somehow they just via down and right here. So they run through a resistor and then through the LED, or through the LED and then through a resistor. Most likely from, like I said, via or something like that. I've got a sticker on the back of the board, so I can't really see if it's running on a separate layer or whatever. But again, this is interesting to look at this way, but totally not the way you would want to analyze a board. I mean, it's only important when you're trying to build your own boards. Otherwise, you just come to the wiring diagram, and that is really where the kind of rubber hits the road as far as what pins do what and everything like that. So before we realized, or before we figured out that the LED number 1 is on RE3, which is the E group of GPIO pins, so RE3, and then RE4 as well, and then RE6. So that's where we get the 3, 4, and 6 for turning on and off the LEDs. So now let's find the switch. The switch, if we go back down to this page, this is the LEDs, and right here is the switch. So there's two switches. Now you can use master clear right here, the MCLR, as a switch, and you can disable the functionality in general. You can disable the functionality of that for clearing the chip, but that is one of the dangerous things you can do. When I talked earlier about your possibility of, by changing settings, can you brick your chip and make your chip inaccessible? Changing the master clear pin to do something different than be master clear is one of the ways that you can actually cause your chip to never be able to boot again. And largely, it's because, like right here, so ICSP, this is one of the debug headers. And you can see it connects to the master clear. So if you're messing with this, you can conceivably set it up in such a way to ignore master clear, and you get it in some sort of a run mode where the debugger tries to attach itself and it doesn't do it correctly. So you can see it's attached to pin 15. It is a valid switch. You could use it. We're not going to, just because safety first as far as this goes. Not that it's a, it's not the space shuttle or anything, but it is a $50 board, and I don't want to be buying another $50 board because I made a software mistake, So we're going to stay on the safe side of that, and we're just going to use the easy button we can get to, which is switch 1. So switch 1, where did you go? Okay, switch 1, SW1. So now what we need to do is we really just need to find SW1, and let's find out what pin it's associated with it. So you can, it actually shows you somewhere else. There's a diagram or a little box that kind of shows you what's available there, just because it is an onboard component. But it's sort of fun just to kind of try and look at this and see if you can find it. So let's see here, SW1. I don't see it there. SW. No. There's the other LED. SPI. Okay. Sorry, I was just looking at the diagram over here. This is for an external oscillator. 24 megahertz oscillator, looks like. You can actually use. Really, the oscillator is really only important for if you're going to be running USB again, because the internal oscillator is good enough for what we're talking about. As soon as you try and do USB, any of these USB connections or anything like that down here, to try and like set up it as a mass storage device or something like that, 0.5% is your leeway as far as staying within spec. So if your USB device has to operate and respond within that amount of time, or it's not considered a valid signal, USB signal. So I don't know, I've been through this twice, I don't see it. So we're actually just going to cheat and scroll down here. And basically, so they've got a couple schematics. This is of the, I think, possibly the EEPROM. Yeah, this is the EEPROM. The materials and stuff like this. Anyway, so, oh, maybe it's up higher. Must be up higher. Talks about daughter boards. There it is. So here's the LEDs. So you can see microcontroller pin is R3, R4, R5, and then the RBG is bank B0, B1, B5. So let's look here. There you go. Switch. Push button name is S1, and it is on RG12. RG12. That's where we're looking. So we can actually just do Control F, RG12, just to really cheat. There it is. I missed it. It was at the very bottom, right there. SW1. Yep, RG12. So let's get back and let's put some code together as a way to read this input and see what we can do with the switch. All right, so I wasn't actually quite sure where to go from here. So what I did is I opened up the PIC32MZ spec sheet, essentially. So this is the spec sheet for the actual picture that's on here. Because at the end of the day, the development board, it's nice because it has the onboard debugger, but essentially that debugger works very much like a PIC kit would, or many of the other debuggers, that really it just sort of is on board and handles that for you. But the PIC kit, the chip, works just like the chip normally would if you had it in any other board, or if you had a breadboard, style at SPIO or SPOC or whatever it is, style that you can actually fit into a breadboard. So really, the reference, what the Curiosity board is really doing for you is it's doing the wiring, it's doing the things like setting the switch up so that standard switch configuration. So it pulls, you have a resistor right here, so it's a fairly large value resistor. It will pull this line high. So this is the microchip right here. So it pulls this line high. So the power, so it will read 1 until you press the switch down. And when you press the switch down right here, what it does is it grounds the switch. So the switch value then goes to 0. Now, you are essentially shorting your 3.3 volts through to ground. But you have a 10K resistor here, which is a fairly large resistor, which really prevents you from putting a lot of current through there, and so essentially burning out one of your leads or burning out your board. If you took this resistor away and you push the switch down, bad things would happen. You would fry something most likely because the amount of current would be incredible that would go through here. It would be literally as much as your computer or USB adapter or batteries or whatever you had through there was actually willing to handle or able to handle. So anyway, so what we have is that. So coming back, like I said, this is the advantage of having a board, is that they do this for you. Otherwise, you would have to do this on a breadboard. You would have to say, where's my line voltage? Let's make sure I get a 10K resistor. Let's put it in line. Let's hook my switch up. And this isn't necessarily the only way you can do it. You could actually do it the other way too, and you could have your resistor here and have your switch here, I think. There's certain configurations you can have that are valid and certain ones that aren't. Like you can run into problems with what they call floating pins and stuff like that, which is if you don't have the voltage on a pin precisely controlled, this is a digital I/O, so it's going to either read it as a 0 or a 1. So 3.3 volts is 1. Well, what's 3 volts? Well, it's going to still call that 1. What about 2.5? Probably still going to call that 1. What about 1.7 volts? What about 1.5 volts? Is that a 1 or is that a 0? You don't really know. And excuse me. The other thing that could happen is if you didn't connect this pin at all, the voltage that can be read off of it has more to do with capacitance or static electricity than it really does with what's connected to it, because there's nothing connected to it. So you can get some really weird things that can kind of happen with these non-grounded pins. So usually that's what they suggest, is they say for any pins you're not going to use, you just ground them out so that they're all just always pulled to 0. So if you have a red to them, it'll always be a 0. Otherwise, you can get some kind of weird things as far as static electricity, static discharge. And, static can come from anywhere. It's one of the enemies of these chips. Literally just, walking across some carpet, and you touch the chip. I mean, you're, 4,000 volts or whatever from static electricity, even though the amperage is very low, the current is very low. It's still, these wires, this stuff is very, very tiny, and it's enough to burn out. So anyway, so now that we know that this is one of the things that the development board does for you, it doesn't actually really matter though, because this RG12, this could very well just be done by yourself, and you could do this on a breadboard, and your chip is going to work the same way. So really the reference that you want to go back to is actually the chip reference here. So I just looked up RG12, and I see that it looks like it's on port G. That is definitely what we want to go and look at. So port G is a good start. You can also notice that it's referenced a few other places, so let's go ahead and look down and see here how they reference this. So output low voltage I/O pins, 12 pins, and these are the pins, RA, RE, RF, RG. So max, standard operating conditions is 2.1 to 6.3 volts. Again, this is a digital I/O, so anything under 2.1 volts, they're not guaranteeing they're actually going to show you a 1. It may show you a 1, it may not. You just don't know. So but 3.3 is what they recommend. So that's what you're kind of going for. But if it's 3 volts, it's 3 volts. It'll still work. So looks like this is just more characteristics continued. Yeah, now it's going to show you where it is on the package. Okay. So really port G, that's what we need to look at. That's what we're looking at here. So, all right. Well, Let's test this out. So the easiest way for us to test this out, to figure out what this actually looks for, is let's just run MPLab again. And let's do a breakpoint on this. And we can actually add a new watch here of port G. See if that works. And let's just go ahead and run the chip. So what I'm going to do is I'm just going to run it as is without pushing any buttons or anything like that. I'm just going to run it and let this breakpoint catch right here. So it'll compile and link and do all the things it needs to do, download it, run it through the debugger, set this as a breakpoint, and then it'll run and halt at this breakpoint. So it says target halted. Maybe this is old. No, that's old. It's still running. You need to periodically clear this thing out or it shows old data. Running, and then it should say target halted. There it is. Okay, so as you would expect, because we have switched the LEDs off at this point, but we're only switching off 3 and 6, I have LED 2 illuminated, which is exactly what you would expect to see. So now what I'm going to do is I'm going to hold the button down. Well, actually, first let's look at port G. Let's see what this looks like. So I don't know, actually, from this definition here. I think it said it was RG12. So RG12 on the 144-pin chip. See, I'm just not sure which one of the port G inputs it is. So maybe it's 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. I would say, if I had to guess, I would say that it's going to be 6. But I don't really know. So let's see. Oh, that's very interesting. They actually don't have them numbered in the same way. So it's going to be 12. Look at that. And you can see the value that it's set is 1. So the non-pressed value, the non-push buttoned in switch value should actually be 1. So what I'm going to do now, so that's exactly what we expect to see. So what I'm going to do now is I'm going to push the button in. I just pushed it in. And then I'm going to hit continue. So what that's going to do is it's going to run through that. It's going to blink the LEDs, and then it's going to come back here and catch again. Now, at this point, these values are not updating. So I can release the button, and it's not going to update any of these watch values. It only does that when you step. So you can actually see that it highlights in red what values have changed. So you can see that the hex value for port G as a whole has changed, but also the hex value for RG12 has changed. So that is exactly what we wanted to see. So we can really tell that this is specifically what we're looking for here. So what do we want to have this do? That is a really good question. We can let's see here. What can we do? All right. So what we're going to do is this. We're going to separate off another pin here. And we're going to have LED 1 be a push button. So whether or not you have the switch pushed or not will determine whether or not it goes on. So we'll just use that as an example, and we'll have number 4, LED 2, just stay on, and we'll have number 6 switch on and off. So when we're switching 6 on and off, we need to clear this out, and then we need to again go back to our hex, our binary to hex, and we need to figure out what 100.00000 is, and that is hex 40. Sorry, I'm not able to do that in my head. I guess that's when you know you're super cool, is if you can do the decimal to binary conversions, or binary to hex in your head. So we know this is port G, and again, we talked about the difference between latches and ports. Really, the ports are an instantaneous thing. Like if we look at latch G, I'm thinking that it's going to actually show. We can do it this way. That's fine. Latch G. it's probably going to show nothing. And the reason is that latches are set by the program. So they're not set by external things. Ports are set by external things. So you use ports for reading generally, and generally you use latches for setting values, sending stuff. So anyway, so we've cleared this out. So now what we'll do is we're going to go to port G, and then we're going to do bits. And then what we're going to do from here is we're going to do RG 12. That's what we're looking for. So we're going to say, we're just going to define a variable up here. We're going to say int pushed equals 0. All right. And then we're going to check and see if RG bits equals 0. So if it has been grounded, and then we're going to update pushed to 1. And this is where it gets kind of interesting as far as the ability to do these things, because when we want to turn this LED on and off, really you're going to have to figure out a way to kind of concatenate in your binary, because we only want to turn the LED 3 on in the case that pushed equals 1. So you can set these bits individually. I'm not sure if they let you do it through this location, or if you just have to do, I guess you can do, I think you can do it this way. Okay. So it looks like you can do it this way. So then it's not quite as cool because you're not doing the binary to hex conversion, but it should still actually work. So let's actually make sure that this does work first. So switch the LED on. So we're just setting, you're either setting a 0 or 1 here, true or false values here. So we're going to actually have 3 of these for each one of the pins. So we've got pins 3, 4, and 6. And then we're actually going to have to duplicate this below here for the pins that we want to clear. So again, we're using clear here, but I think we're going to have to, since I don't think there's a latch clear, I think we're actually just going to have to decide which ones we want to set back to 0, with 0 being essentially an off state. And what we decided is we're going to keep 4 on always. So we're going to remove that. And then this is going to say switch off LEDs. So let's just comment this code out, Control/comments code. And I'm going to stop this. So right now we are not doing anything as far as reading the switch. It may throw a fit about that. I'm not sure why this is underlined. It could be because I'm not using it anywhere. So maybe I'll just leave that in. I don't know. We'll see if it compiles and see what it says. Could be that I need to do like signed or unsigned or integer, or I'm not sure exactly, what they're calling. It's C, but it's, a little different. So, okay, it looks like we have some sort of an issue here. Int pushed. It says unused variable pushed. Right. So, actually, I commented out the wrong part. So what we just need to do is we just need to use it. So we'll just set it to 1. Even though that does absolutely nothing, it should actually take away the warning here that we're not using it, because we are initializing it and then we are changing the value. So even though we're not actually reading it or doing anything with it, it's not being productive. It is actually doing something as far as operating. Okay, pushed. Set but not used. Pushed. Int pushed. Interesting. Well, maybe we have to use it. So I guess we'll just run an if statement and if pushed equals 1. See how complicated this can go. And then I could just do an if with nothing in it. Sure, we'll see if that works. Maybe it'll work, maybe it won't. I guess we'll find out. Because we're actually reading from the variable, so maybe that's one of the things. If you just set a variable we never read from it, it could say, well, you're not using it. Okay, so even though this doesn't actually do anything, there's no code in there, it has removed that error because we are reading from the variable. So you guys might actually not have the same problem. The reason that that is showing up too, I'm just going to kind of show you in here, is if you go into, I think it's GCC, I can't remember exactly where it is. It's under General, Optimization, Preprocessing, Isolate. It's just, okay. It says make warnings into errors. So if you take that off, you can actually take that one off too, but I'm going to leave the additional warnings on there. Then you can actually remove this block here, and it should compile. The reason is because an unused variable is a warning. It's not something you're supposed to do. It's not a best practice, obviously. It's an optimization you can make in your code. But, oh, yep, still there. So, oh, see, that's the difference. So it actually shows up, but it says it's a warning. So, warning unused variable, but it does say build successful. So, you can get away, if you don't have that checked, you can get away with running it without that. So anyway, so this built, so that means that our syntax seems to be correct, but let's go ahead and run this on the device, and we'll see if it operates in the fashion that we expect it to be operating in. Still programming the board here. Boot configuration to memory, so we're almost done. Running. Target halted. All right. So I made a mistake. These are supposed to be zeros. Oops. All the LEDs, we have 3 LEDs lit right now, so I'm like, yep, that's definitely not what we want. So let's try that again. Those should be set to zeros. To switch off, 1 being on, 0 being off. Alrighty, I believe this is actually working. I'm going to go ahead and turn on this breakpoint right. Well, I'm just going to disable this breakpoint. There, all breakpoints, and hit play and see what we got. Yep. So we still have LED 1 and LED flashing. So LED 1 and LED 3 flashing. So even though we've converted here to the latch E bits as opposed to doing the binary thing, which is super cool, but this is actually probably a little bit easier to, it's easier to control for one. So you don't have to specifically go in and set that. So anyway, so I'm going to go ahead and stop this. And let's make a few adjustments here as far as what we really need to do. So we're just turning LED, and this is LED 2, LED 2. We're just turning it on. So so we actually don't need to run this in the loop. We can just put this up here and say, yep, just turn that sucker on and leave it on. That's it. Okay, so now the blink is really around LED 6. That's really the one we want to blink, and that's it. So we're going to actually remove this code as well from up here. So we just have LED 6 there. Paste that, so now I've got both the on and the off code for LED 6, or LED 3. So, and then we've got the delay, huge delay. Okay, so we're just going to put this code at the bottom. So, pull this in. So essentially the code that we have above here is just for pin 6, so LED 3, and it's just determining. Oops, it's actually about the huge delay. It's huge delay. All right, so we turn the pin on, huge delay, turn it off, huge delay, do something else, and then loop back to the while loop that never ends. So what we want to do here is let's remark this or unremark this back out and check and see what we have. So this we already figured out is correctly checking to see whether or not that button is pushed. So if the button is pushed, we want to toggle this. So if pushed equals 0, there's a lot of ways you can do this. If you wanted to be fancy, you could use the modulus operator and do like equals pushed +1 mod 2, I think is what you would do. I don't know if that's even the syntax for C. But it can be complicated just to sort of understand what it's even doing. So I'm just going to make this super simple and just say, okay, if it's been pushed, if, and then we're just going to check and see if it has been pushed equals 1, then we're going to set pushed equal to 0, and if else, not if else, just else, we're going to set it to 1. So this is not super cool programmer logic, but it is very concise logic and very easy to set breakpoints on. In fact, one of the things you give up by having condensed logic is your breakpoints. And another thing to keep in mind here is that this is a C program. We're not writing this in assembly. So this is going to go through a compiler, which will probably optimize this to be something else. So you don't really necessarily have to be incredibly worried as far as how optimized you're going to be, especially with logic, like something that's as simple to transform as this into a modulus or something like that. You know, again, it probably wouldn't convert this into a modulus, but again, we're not really too worried about processing time at this point. So it's really one of those things. I am very much a proponent of optimize when you need to, and not just when you can, because you can always optimize. So, all right, so, okay, so should be on. Just realized that my variable here is not really the right way to think of this, because it's not really if it's been pushed, it's really if it should be on. So if it's pushed, it's going to be 0. But if it should be on, then we should say, well, now it should be on, now 0. So no longer should be on. So really our check here is, should it be on? And we can sort of, again, we could do a true-false thing here, but we can actually kind of condense this and just put the variable there. I believe it'll let us do that. And then this is just a switching the LED, and it's setting the bit constantly. So every loop, it'll say, should it be on? Should be on, set the bit so that it should be on. If you hold the button down long enough, you're going to have to hold it down for a second, because it's going to have to go, well, true second. Probably like about 500 milliseconds is how long you have to hold it down. Because you need to have it held down through one cycle, because it's only going to read it specifically right here. So if you have it held down from the start of this to the end of this, and then you let it up, then it's not going to find that it was called. So you just want to make sure that you've got that you understand how this works, so that how long you need to hold the button down in order for it to correctly operate. So let's go ahead and see if we can build clean this, see if there's any compile errors, see if it complains about should be on or anything like that. I think I got it all correct, but you never know. All right, looks like it's running, so let's go ahead and debug this. And let's go ahead and put in a breakpoint right there. Now, a note on the breakpoints. most people that are used to programming in other languages like Visual C, C Sharp, or PHP, Java, Python, whatever, you're used to being able to dynamically set your breakpoints. Here, you have to set your breakpoints before you start running. So I barely snuck that one in because I'd already hit the button to go, but it actually did take the breakpoint. The reason is because these breakpoints are actually set on the debugger that's on the chip. So it actually reads what line of code you're executing, the debugger does, and says, okay, you hit this spot, or again, it's probably not so much that it reads in the line, it probably actually inserts some sort of an instruction into the hex that says debugger here or something like that. I'm not exactly sure exactly how it does it, but somehow it does. But it's just important to note that you need to add these breakpoints before you start. So let's see. Let's put that in there. Oh. Okay. Well, it's high, so it equals 1 right now. XL1. So I did not push the button. So I'm going to, let's actually just run this. I'm going to step through it, F7. So it should be on, what was that set to? Should be on int 0. So it should be on, so LED 3 should not be on. So let's just go. Excuse me, LED 1 should not be on. Yeah, I was going to say, because LEDs 2 and LEDs 3 are illuminated. So 3 is the one we're blinking, 2 is the one that we're setting right here to be on, and this is LED 1. So it's important to know, so we know what we're doing here. All right. So I'm going to hold the button down, and I'm going to hit run. So now our breakpoint should pick up here in just a second. So again, now that we've caught the breakpoint, I can release the button because the value should already be loaded in the register, which it is. So that's why it hit. Honestly, it would not hit otherwise because it would equal 1. So now it says should be on. I believe that was set to 0. So it should be on at 0 right now. And if we hit F7, it will, oh, F7 is skip. Should hit, no, F7 is not skip. I don't know exactly why it didn't do that, but it should have actually hit that line of code right there, but you can see that it did what we were talking about doing because it did set it to 1. So now this line of code, if I hit F7 again, should turn on LED 1, which it did. So we are good to go on that. So I'm going to remove this breakpoint. Remove all breakpoints and continue. All right, so now we're running. Yep. It operates exactly as we would expect. So I am going to take a short video of how it operates so that you guys can all see. And yeah, another success. So that's some good luck today getting things working. Alrighty, we have this program running now on our Curiosity board, PIC32MZ Curiosity board, and as expected, we have LED 2 fully illuminated because we moved that code above the loop, so it just stays illuminated at 100%. And then we have LED 3 that is still flashing, so that's flashing due to the while loop that we have and the delay code, the huge delay code that we have that's running 20 million cycles each time. So it runs 20 million cycles, turns it on, runs 20 million cycles, turns it off, and then that's basically what we go. So when we push this button, it's not going to be as responsive as we probably want, and the reason is that we have to, well, it was there, but we have to hold it on at least for one flash, because there's only a certain amount of time
one line of code that is checking to see whether or not it's on or off, and there's many cycles because of the delay code that run before or after. So we are only checking at one very specific point in the code. So for example, there it was fast responsive, there it didn't respond at all. So you can actually hear that I'm pushing the button several times with no result. And really the reason for that is that you have to keep the button pressed down while the code is running over the line that's checking to see if the button is depressed. So if you hold it down long enough, it will always illuminate. And you can actually see if you hold it down forever, it'll flash, essentially. And the reason is that it's flashing at half the speed of the other flash, because the other flash is running, the yellow LED is turning off, waiting, then turning back on, and then waiting, and then the button code is running. So the button code only has the option to turn on or off once every while loop, where the yellow LED is actually turning on and off in one while loop. So that's why you have the speed difference here of the flashing. So again, not the most reliable way, not the way you're going to want to design a microwave that's not responsive enough for consumers or really even for personal projects. It's probably not the way I would recommend it. There are better ways, and we're going to delve into those in future episodes. Now, the way that you may think that to do this would just be to remove the delay, and if you did that, then your switch code would hit more often. The problem with that is that when the switch code hits that often, you have to have more complex logic around how you are capturing the press of the switch. Because humans are so much slower than microchips, pressing this button down, if you had the logic running without the delays, would be held down for thousands or tens of thousands or hundreds of thousands of cycles, and you're going to get some unstable consequences to your LED illuminating. So it won't necessarily toggle on and off like you want, because it's reading the switch so many times in a row. It's not just reading it once, it's reading it, like I said, 10,000, 100,000 times. And it's really whatever state it happens to be in when you lift your finger, that is what state it's going to stay in. Otherwise, it's going to go on, off, on, off, on, off, on, off, on. And if it stays on, then it's good. And it's doing what it's supposed to, but it's a 50% chance, essentially, that it's not going to do what it's supposed to. So I'm going to make a short video kind of showing that off.